in my opinion, is one way of casting the problem, which is usually working well on embedding representation learning and all that. For example, maybe you can add that translation actually has two ways, right? The machine translation and the human translation are very different. I can imagine machine translation could be done in a closed way, which is the mechanical mapping of source language target language. And right now, that's what's happening. Okay, you have a big kind of a transformer in the model in the middle, and I just do mapping, which does all alignments, representation, embedding, and that. That's not how human translate. That's why we say when, for example, I train people, you train a MT model, you get some data representations. Can you use the same data representations to complete another task, which demonstrates your understanding of the semantics? Most likely it's not. And that's because it's a dividend, but it's a cost you pay actually, or penalty you pay for end-to-end or close to
exactly.
And not trying to understand.
Yes.
So in a sense, I'm not ready to accept that you have one principle or a arithmetic or a coding principle to define AI.
No, this is not a general.
Yeah, as you mentioned, for example, logical inference, symbolic inference,
yes,
and all that,
yes,
are not ready to be encapsulated in fact in this framework.
So there's two things, right? So one is that today we only talk about the visual data, right? In fact, even the visual data we work with is just already, they should have a low dimensional manifold structure, right? They're actually already aligned. Right? So they're not like, transformer probably have to handle the alignment of the data. Here is a simple cases. The structure we're looking for is relatively simple.
I think that the closed loop framework of classical holdings numbers can be actually tracked. Why is supervised learning? That you have input and output mappings. Yeah. You can actually, in fact, in the original probabilistic inference model in graphic models, you have the journey model and the version model going backward. It's exactly the same thing I'll say in the data center. The other scenario could be auto-infer where you regenerate one, that you have one thing and then you have the same thing in here, you basically reproduce that in your auto-infer state. Yes. But there are many tasks which are completely open. For example, when I translate or when I debate with someone, I actually don't know what he's going to say to me. Yes. I'm going to be completely open and my thinking and my encoding and my reasoning is going forward without a target.
Yes.
And I think that in AI right now, a lot of things are stuck in that area.
Yes.
How to actually build a machinery that is open-end and handling unknown thing, and also without even getting a feedback when you do something. And how to scale that. Something I think is very interesting.
Yeah, I agree, but that's a task may be open-ended, but then the learning to do the task well can be a closed loop, right? That's why we even debate and we train. We learn, that's a game. Actually, you actually really need to read actually this is actually one of the
so I think you can agree on the following. So learning, learn what is about learning representations. Right? You don't learn to solve a task. But that's actually
yes.
Exactly.
That is the game. That is you have to learn that in a game. You have to assume certain adversarial.
You learn certain knowledge, just like a human being, you learn in college and certain knowledge, in this case, representation. But then, when you solve tasks, there is a open space for you to
extrapolate
and to innovate. And that actually leads to my second question, which is often downplayed in the entire field of machine learning and AI, which is the operationalization. Because when you solve open task, when you solve it, you need to have the freedom and ability to combine and operate. So sometimes I think what I learned from deep learning, which has many negative sentiment to that, as a dark matter, but one thing it did very well is that it is a very optimizable. Yeah. That you add a component, you combine transformers, you put transformers upside down and form a detectron or something. It allows people to compose, to synthesize, right? But on the other hand, statisticians and traditional machine people are very bad at it. They say, yeah, here's a loss function, here's a framework. You have the coding theory, you have compression theory, you have the probabilistic divergence model and so forth. And then you are, you just place a model and then optimize. But this don't work model and the algorithm. It's the whole work of somebody else's research, which is discounted.
I agree. See, you got to agree, right? The operational and compositional, which was precisely the strength of system theory, right? Systems is exactly about how system gets concatenated, right? Synthesize, parallel, loops, and so on. System theory is very good at, but somehow system theory in the late 90s get distracted. They care about system only when those components are transparent, are analytical, right? Which is a big mistake. Right? In fact, if you go to read Hinton, what Hinton was doing in 1990s, late 1990s, system identification. He tried everything, right? EM algorithm, he was playing with those. And we have course he gave up, right? Because then he just started to go backward to neural networks. Because that allows you more flexible to map in the input output. Because you might get sick, even I got sick, right? Every time I have to write out differential equations. If you don't have a differential equation, you cannot say anything. Turns out that's exactly what you said. Right? We have the deep learning actually made a very flexible toolbox for us to model, make it operational to model the system, model the input output map. But still, it's a segment. We still need a bigger, better principle to how do we synthesize to build systems.
Actually, that's a word I had a debate in the past with someone, about the word attention. So if the deep learning model becomes small and now viewed as a component, okay, as a building block, and then the bigger problem needs people to even synthesize multiple elements on top of that and so forth.
Yes.
Do I do care basically even what is inside deep learning, rather than view it as just a little black box as much as I could exploit it, and then I worry about how the interpret it. Because for example, right now we take medicines. Yeah. We take food. Do I need to even know what is in the medicine? As much as it tells me that
that's something. I absolutely agree.
And also even I challenge also the so-called explainability. Actually, I have to be a biologist. So I know biology more than many other doctors. They claim that they are giving me something that is explainable. I said, really? Yeah. You really know that aspirin is acting on a certain molecule, control certain organ, and therefore cure me? They don't. Yeah. They actually are also
tested. Yeah.
They give their hypothesis, which is for the psychological comfort that they thought it is explainable. Yeah. But to a molecular biologist, that entire explanation is done. Yeah. But I still take it. Just because it's empirically good. So now, if I'm a criticizer of deep learning, but I want to give the fact of what if that deep learning thing, for example, the word model, give me the good embedding of the words, of everything, then I will use it as the building block of my next thing. That
absolutely
be totally fine of not asking for why word is just repeating.
Absolutely. So there are different layers. One is to use deep network. For example, any of the segments, FM or G, generative or discriminative, they're themselves already very useful. But what I'm trying to say here is that we still need to understand what function they're to achieve. So we also potentially have criteria to say maybe we can improve. Even BERT maybe give something we can already use, but there may be things we can also further improve. What we want to often, or compare with potentially better, if I want not just to synthesize the signals, I wanted to do other tasks. I may want to know what I have learned, right? Grammar, which part learn the grammar, which part learn the meaning, things like that. So one thing we learned from this is that precisely the system is only trying to represent the data. It doesn't really quite tells you want to use this for classification or for other tasks, right? So that's why it's shared here. And this is a simple example. I'm not saying this is all the problems.
We have another slightly philosophical thing. If the task is higher level and compositional, then do we even care how good the embedding is to a certain degree?
No.
Right. So then.
But we need to understand theoretically how good needs to be. You know what I mean? Give some kind of quantitative. Right? In fact, this is one belief. Why we do things in closed loop in control? In fact, control always knows. There's no way you can identify any system precisely.
Yeah.
Right? That's why nature already figured out, right? We can never identify this, but as long as in the neighborhood, right? As long as the error is reasonable, we can correct it.
Yeah, but
right?
then
So you need higher level. First of all, you need to understand how close those system gets identified within certain neighborhood of the truth. Second, all control theory says within that neighborhood, then we can guarantee a closed loop system. The fixed point algorithm give you the correct solution. No disaster would happen.
Yeah.
So that's kind of guarantee we need to build for
that
networks.
definition is very tricky, right?
Yeah.
For example, embedding does not have truth. It's basically just we usually need an external kind of auxiliary job to determine the quality. Right now, which is classification, or imaging. I often challenge my colleagues in that case. Do you really care that a particular object condition, needs to be very, very accurate in order for me to do other things? Like Akio yesterday gave an example over the weekend that you have this impressionist thinking that in the middle there's a color block, which you have no way to classify it. But for people who stay afar, they will know it's a locomotive and something else. Right? So in a sense, I challenge the very kind of design of the experiment, how we even qualify, the quality of the representation or embedding in the middle, without the context of the bigger data. My context will be Xing understanding. Then do I need to even know everything in the pixel level? Earlier on, I also had other debates with people. I say, if you are not doing Photoshopping, why Photoshop? Why do you even care about pixel level classification accuracy? You don't care because that's not needed. We're human beings, when we recognize objects, sometimes I don't actually see that clearly. I can still recognize it's a horse or something. So that's actually the challenge right now. We actually have the right framework, even in evaluating, that lower level.
Eric, you are absolutely right. So actually, I'm writing a position paper. I'll send it to you. All I'm saying that today, even the past 10 years, even what we did today is according to Wiener or the framework, still at the individual low level signal data structure level. Honestly, nothing beyond that. On top of that, really how language evolved, symbolic, what you say, that the parsing the scene, even causal relationships, even logic arises. That has a lot to do with intelligent beings to interact, social, communicate, transfer knowledge. That level, honestly, I don't think we have anything, except that we can manipulate, use a neural network to manipulate, transform from one domain to another domain, to learn some useful input-output relationships. That's about it. But in terms of really they're already good structure. Actually, neural to give credit, right? They can capture good structure already in those data. But whether to the extent of why the structure emerge, or what there's something intrinsic behind it, we're nowhere near to get those things at this point. I'm not even claiming even this framework, but there are something might be universal about closed loop. There are two principles. Why is it? You can think about the closed loop is kind of very universal in nature, right? The brain memory forming, the muscle control, even DNA, right? RNA to DNA. It's called transcription. It's a closed loop transcription. So this is sort of a universal structure, I believe, is nature figured out how do I copy one thing to keep what's essential, what matters to me, so that I encode what is essential and in a very compact structured way. And so I can pass it on or can use it later, right? So this kind of, this closed loop, how do we transcribe those visual data from different levels? Maybe it's a loop after loop, right? Yeah. From, low level to higher level, even from outside the world globally to that. So there's maybe multiple layers of abstraction to distill the information in this framework.
That's what happens for dynamic systems.
Yes, systemized abstraction. As I said, system people has the right framework to study those composition, study how the complexity is dealt with, but they really distracted in late 90s, right? To just working with analytical form. They really didn't see the computation. A lot of things, just like Hinton did, right? Hinton tried the system ID, right? Yeah, one of the things that he didn't work, right? He wrote a lot of papers about it. Yeah, remember, he didn't give up. Let's just give up. Let's just do the system ID, use a neural network, right? try to map even use a black box, just make the input output good enough, right? He actually embarked on that. He benefit from it. Like this is exactly what the system people, unfortunately, it is a system, but they don't want to treat like that, right? They don't want to study that.
I remember there was a small debate in one of the, I think the input causal inference conference, trying to establish connection of causal inference system to like the infrastructure at hand.
Yeah.
And again, the moderator was trying to help me to bring my work to the statement. He asked the following question: what is a system? Because I branded some of my work as system theory. What is system? Guess what? There's a whole lot of answers which is kind of entertaining, right? Some might say system is basically within and also the environment, and because it's a system, yeah. And then some people say system includes social feedbacks and so forth, and then so let's try to get philosophical. I say, hey, what I hear is that system is a universe. You don't define a boundary of the system, then everything becomes a system. It couldn't even start a intelligent conversation because now that everybody claims that we system theory. Everybody, but all the people who never write a code in a system, who never actually tune a machine, call themselves system learning people.
Yeah.
I'll say, okay, I'm giving me all of my job because I thought I'm unique. Now you are actually saying you are doing the things as I do. That's actually very interesting, right? So I think that what's needed right now is some kind of a boundary and a clear definition. You have to have multiple areas, but you need to also know that there is a boundary that you are crossing the area and doing the other. But I think what just raised by the system people doing something analytical only, not computing, is probably a consequence of that lack of boundary and respect of the boundary.
Exactly.
They thought they are doing the system, but they never touch the system yet.
Yeah, well, the system can mean different things, right? So that it's not just something you can write on different equation in the system, right?
Yes. And the world becomes too generic, and it becomes a universe, and the world is not even informative.
Yes. So I mean, that's why Harry Shang and I were writing a paper together, trying to do sort of position paper, perspective paper. We're trying to put some of the ideas together. So the one thing common I had with Harry Shang is that we are both trained as a control. We both study automation. We're undergraduate student. That's why we started collaborating on some of the things. So we all realized that even so reinforced learning using this framework, but this is also, you can see the optimal control uses exactly the same framework, right? What we think answer your question of system. I start to believe that at least in system, there's a definition of what we mean by quote unquote system is that system needs to be autonomous, right? So basically there's no, except its own resource, its own objective, right? It should be autonomous, right? It should take nothing outside, only observation from outside. Then there's decided by its action, right? Its action and all defined by its own internal objective and internal resource.
That's always a very, very important and interesting question. When you say system becomes autonomous, I still don't see right now any even thinking about how a piece of code can autonomously enter a computer, load it itself, and start to train. Because otherwise, if you talk about a system that is only software and no hardware, that's not a system.
Yeah.
And the way human being has the brain, but also have the limb and the body. So therefore, we enter our code into a body autonomous.
Yeah. So, well, you can think about it. The system is not that self-closed, but it actually has a clear interface to the.
That's things that I think people probably went too far in already without even some basics. How to even put together what it takes a piece of code to self-load it itself.
Yeah.
Solving that basic thing before we talk about even the first two.
So I really I should try to read the Nobel's winner's book, where he has said that there are two characteristics about something you can call it alive or intelligent. One is that the ability to learn. The second ability is to reproduce itself, right? So that's the definition, universal definition of something alive or intelligent, right? So right. So if the code become alive, which means first of all it can learn, it can evolve, adapt, right? You can think about the loop sort of doing that, right? We learn from reinforced learning, so kind of. But the loop doesn't reproduce itself. We have to put itself for it, right? So for this to become alive, it has to somehow reproduce itself.
So yeah, let me be very honest here. The something that is very, very optimizable. Because I don't imagine a aircraft reproduces that ever.
Yeah.
Okay. And therefore, building series on those kind of things becomes a fantasy. It's more like going back a bit and to be try to break the problem a little bit closer to what is really feasible.
Yeah, the world has very different problems, and a lot of things we don't need intelligence. But I think if a lot of the framework we're trying to build, I think it's probably for people who are interested in really robotics, probably need to think about those kind of problems. Right?
Yeah.
Robotics, I mean, the individual agent needs to be very, very autonomous in the environment. Second, that maybe in the future we can want a robot to build themselves, right? Reproduce themselves in some way. Probably. And also the one thing got us very interested in this kind of problem is that I work on computer vision, right? I'm very frustrated with robots, right? Because see, all the robots go to the room, scan, right? Everybody's doing some demos. I have another robot. I come to the same place. I have to scan again, right? And how do they share? Human, we use symbol to share, right? If I'm in this building, ask where the bathroom is. You can draw me a very simple. I will never get lost. How in the world? I mean, robot needs to communicate at that level, right? Few bits of information. That's it, right? So all the information gets shared. But right now, it's just darn point clouds, a mesh, a voxel, right? And then let's just align them to ICP. And Jesus, that's just unbelievable.
There's a technical question here, where to start, right? Yeah. Let's say we even simulated two digital robot dimension. I think that task should go first to the computer side.
Oh, in the simulation.
Yes. I don't think it's fair to ask what is this that we as a computer science haven't figured it out. We already asked the hardware. That's the whole point.
I agree.
The blame is like the other side of this and that. I actually want to shift the blame for ourselves. I'm always a criticizer of ourselves. I think the we as the AI people as statistician didn't do enough our own job in giving people tools yet.
Exactly.
But that's actually I don't see effect in our in yours and
in fact, even the robotics people are learn big lesson from, a lot of things you can learn from simulation. If you do good simulations, right? A lot of things you can already solve your 90% of problems. If you cannot learn the direct control with a well-simulated controlled environment, how in the world do you play with the mechatronics, right? With additional layers of complexity or uncertainty, right? So this is actually very, very good. So one thing I can tell you a little bit of why, even we consider this. I got stuck with this big problem to compute to compare X and X hat for about more than almost a year. I don't know the solution. But I do think that the thought you put there is very, very useful. We need to do a lot of thought experiments first.
And also
right?
Into the for example, whenever I hear people say reinforcement and so on and so forth, I actually was turned off the safety control because there are so many little things inside reinforcement, which is not just the elements equation and the policy equation.
Yes.
Okay. There are a lot of designs of encoding the action.
Yes.
Right. Encoding, maybe even not. I'm not talking about this embedding. It's real kind of operational encoding of the reward functions or the state action mapping here. Many people who are doing sort of full claim to doing don't even know this terminology.
Yeah, so that's what we
exactly.
So
this is a problem. They over corsify.
Yes, that's what the problem is. They don't appreciate the actual computation or implementation of even the component. That's really the mistake. The control system people made a mistake. Right, and so actually that's why this is a figure I draw with Jitendra Malik, Shankar Claire. We actually did a course called the Integration of Perception, Learning, and Action. Right, so this is I did a little survey really about optimal control and reinforced learning. What is similar, what is not, right? And there's a whole talk. If you want to come on our website, you can say, right? It precisely tells people, control people, what you guys are missing, okay? You talk about encoding, right? How the high dimensional to low dimensional embedding, and also even the lack of analytical solutions, right? Modeling of the system, but RL is trying to model that. Control didn't. Yes, it's under a similar path optimization principle, but the implementation is very, very different.
Another difficulty I run into is getting this good side here and then talking about you right now. No one wants to spend any effort on data. They thought I'm this noble person, some slave to prepare data for me so that I turn the key and run the experiment. Again, data processing is also part of machine learning and AI, but nobody wants to do it. They thought it's unnatural, and therefore, so in fact, that probably is equally true in computer vision. Computer vision basically, this whole area is led by data. ImageNet basically dominates maybe 90% of applications in the whole field, but the ImageNet was prepared by someone. And it's actually really serving your goal. Do you really need that data? Right? That's a problem researchers should ask in the first place. We human beings, as a human learner, we prepare our own data, but we're not actually, as enable we become old enough to prepare our own data. We know what to choose. And right now, I think that this whole field of research is reliant on suppliers of data to the point that some of the data was itself synthesized by another aggregates. We studied that. So these are the issues I wonder, for example,
exactly.
The whole framework right now is that helpful to even shed light on how data can be processed before even they enter any system.
Yes.
Right.
Yeah, I completely agree. I mean, this is just to ask us a question: what do you really want to learn, right? What is the target of learning itself? The purpose of learning, and also give another even extra layer of uncertainty, right? I started when I was a graduate student. I started computer vision. I spent, the helicopter landing. Do you guys think which part is hardest? Control? No, it's actually not. Right? Right now, differential equation is just another, a month's work. Right? Calibrating the camera. Every single thing. We get into physical fights between students, right? All the mechatronics symbol them, right? Camera gets in, right? Every time touched it, we get a physical fight, right? Because it means I have to spend another half a day to recalibrate everything. Okay. So to get the hardware prepared, get the data prepared, then you know what you want to achieve because that's the accuracy you have to get, right? Otherwise, you crash, right? Helicopter crash. Right? So those are the things I think. Honestly, guys, this is nowadays if you want to have an impact, you have to know where the real problems are, right? Writing, that's why there are 10,000 papers submitted to NIPS because their bar is too low, right? Everybody working on the same darn data, right? They're not making any innovation whatsoever. Right? Even not thinking of the problem from a different angle, because you don't think about what you need. You think about what can make the reviewer happy, right? That's terrible.
How we train our students now.
Yeah.
The first thing, how much time you actually spend in preparing your experiments.
Yes.
Versus writing. Yeah, you're actually the same story with I was a physicist, so my thesis was about the study the atomic, optical spectrum, of certain radiation. That was basically an atomic, physics experiment. But I actually spent 2 years building that later.
Exactly.
Okay, purchasing wires, blowing tubes, and all those things. And we spent a lot of, in literally 2 years building this whole laser system. And that experiment, that shot, took just a week.
Yeah.
Okay. And that analyzing that shot, even shorter, we actually have all the visual compare right now. It's called moving analysis. We roll something or they force direction. We want that shot to prove my analysis. That's how physics is done.
Yeah.
That moment of experiment and the methodology is very short.
Realizing things is hard.
Right here, I think
conceptualize things is easy, right? Implement and really realizing things are hard. I mean, you can see that that's why because we had this when we were graduate students, we're building these helicopters, right? And this now there's drones everywhere, right? DJI or even the 2 drones fighting over Ukraine, both from Berkeley. By the way, even the Turkish company supplying the the drone for Ukraine, and also the Russians using DJIs, right? They're from the Berkeley, right? Because 30 years ago, there's a team of people decided to do it, right? You go through, cracks everything with very limited computation. You try to control the helicopter. We land on the battleships, land on different things, make that mature. Of course, it takes years to mature, make it easy and simple. But those are the things, if you want to make an impact 20 years from now, you just cannot download some public data sets. Think you can do something imaginary, magical with it, right? You have to, even industry these days dominated the landscape, right? Because they have their own data. They have their own systems, tools now, right? We academia has a hard time to compete now. With the same game they're playing. But of course, then we have to define new games, right? I tell my students, right? They have DNL, right? The machine, we have the null, right? So that's only we have to find something we are good at, right? To compete, right? What Google people will be missing, what the Microsoft people will be missing. That's your own opportunities, right? You cannot compete with, your weakness against someone's strengths, right? But hopefully here you have more resources, you can do more exciting, more ambitious things. But nevertheless, right, try to be ambitious, try to be different, right? Think about it in different angles. I think one thing I benefited a lot from this discussion with Yang Kung was that, if everybody's about fitting the labels, right? Can we just shift it? That's all we did. We changed the perspective a little bit, right? All the information, there's a whole theory developed to try to explain data fading, model fading, right? Information bottleneck is trying to explain what happens. Yes, it fits that. That theory explains data fading, label fading perfectly. But it's missing a piece about learning, right? What if you want to learn data that works for the classification, definitely not for generating. Right? So those are the things you realize. It actually turns out things actually in research can actually become very, very simple. Right? And to really look at the things that people obviously the blind spot of everyone. Right.
Okay. Thank you so much.
Yeah. Oh, Eric, this is for you.
All right.
Yeah. So I gave you some homework.
I guess.
Yeah.
And everybody, I will have to read it.
Thank you, Eric.
Yeah, so that's a gift. Thank you for your gift as well. Yeah.
Thank you very for an excellent presentation. Insights and the discussion also brought a lot of good things. Yeah. One of little question before I go. Yeah, and or two more questions. You spoke about non-stationary type of data in sets that are very, very high dimension. How about data that are moving in time, that are dynamic? Are you able to expand this to that particular?
See, I mentioned the end, right? So yes, some of our working on the obviously, right? So here is all we just example all static data, right? Images.
Yes.
Right. So there are structures. The one type of structure is after. Of course, with sequence data, there's both structures. There's temporal structures,
yes,
right? Sequence, images also, right? 2D
speech,
location. That's what actually transformer is good for, right? But now if you think about it, transformer is not doing anything different, right? Must be compressing something, right? No, but if you have a sequential data, you cannot simply compress it, right? Because this is one sequence, I say the same sentence, 5 seconds later, it's the same darn thing. But you cannot compress as it is, right? What you should do, you have to align them.
Mm-hmm. Yeah.
Hence, that's why transformer does a positioning code. Guess what they're doing? They must be compressing, align the data as well as compress it together, right? Go read Wiener's book. The first thing that you do with any time environment system, you do alignment. That's why he's, all the Talmudic classes is trying to do that. That's why he brain compress things in frequency.
Yeah.
That's why position coding is cosine sine. Why? Because even in a Redu network, you can read our paper on the Redu network. If you compress all the data with a shifty variant, treat all the shifty variation together, you compress them together, the gradient descent operator automatically becomes convolution, becomes shifty variant, becomes actually it's efficient to compute in the frequency.
Mm-hmm.
It's not for you to decide. It's the nature, the job. You try to compress, because that's the best way to compress. Okay, good. Thank you very much. Sorry. Yeah, sure.